I do want to hand out is I'm going to hand out this sample document, just as I find that people are more likely to look at it if they have a paper copy. So get these out also. So this sample is, I think, like 25 questions long. That's about double the length of what I would expect the midterm to be, though I haven't written the midterm yet. So, you know, if you look at this and you decide you probably could get this done in like 2 hours, okay. I'm not saying you should like sit down and try to set aside 2 hours to do this. Oh, and this too. So some folks in this class have accommodations to give them like time and a half on the exam. You need to get that scheduled through the testing center. I don't think it's like tight timing-wise yet, but getting that scheduled sooner rather than later would be good because I have to like approve a thing before they'll finalize it. So get those things scheduled. If you're not sure how to proceed and do that, then come talk to me at some point. Send me an email. I can send you some information. Neato. So let's begin. So I want to start in on a new class of functions, the so-called rational functions. And let's start by just asking a question I've asked before. Are these five functions polynomials or not polynomials? F of x equals 5. Polynomial or not polynomial? Polynomial? Not a polynomial. Aha, trick question. Constants are polynomials. A polynomial is anything of the form like ax cubed plus bx squared plus cx plus d. Well, if all of a, b, and c are 0, then you just wind up with a constant term. This is what's called a degree 0 polynomial. So that is a polynomial. What about 1 over x? Polynomial or not a polynomial? I don't remember this button. Yes, it is. No, it is not. Perfect. Yeah, you're not allowed to divide by x in a polynomial. Four x to the fifth plus 4x minus 2. Polynomial or not? Polynomial? Yeah, right, of course it is. It's a sum of coefficients next to non-negative powers of x. What's the degree of that polynomial? Degree 5. This one, x minus plus 1 over x minus 1. Polynomial? Not a polynomial. Yeah, right? You're not allowed to divide by anything that has to do with x's. If I were just dividing by like 7, it would be a polynomial. But I'm not. I'm dividing by something more complicated. What about this last one? Polynomial or not? Polynomial? Yeah, right. You would FOIL it out. You get a degree 3 polynomial. So let me focus on these two, the ones that I said are not polynomials. They look like they have to do with polynomials, right? 1 over x is a constant polynomial divided by x. It's like a quotient of polynomials. Same with the other one. So if we can understand polynomials, probably we can understand polynomial divided by polynomial. That's what we're going to start studying today. Those are the so-called rational functions. A rational function is a ratio of polynomials. Same as a rational number is like a ratio of integers. If you can write a function as polynomial divided by polynomial, it's a rational function. I guess you better have q of x not equal to 0 if you're going to divide by it. Can't divide by something that's 0. So let's play the same game of identifying are these rational functions with these 5 examples. This first one, is that a polynomial divided by a polynomial? Yep, so it's a rational function. How about this next one? Is it a polynomial divided by a polynomial? Technically, yes. And we're mathematicians, so technically is yes. What's the denominator in this ratio? 1. So that's a rational function. Any polynomial is a rational function. Just like the constant function is a polynomial, you just shouldn't think of it as a polynomial because it's a member of a much smaller class of functions that you can study more easily. If you see just a polynomial, you can study it as a rational function, but you can also study things that are more easier than including. How about this next one? 1 over x cubed minus 3. Rational function? Folks for yes? Folks for no? Well, let's see. It needs to be a ratio of polynomials. Is that a polynomial? Yep, it's a constant polynomial. And that's why I want constants to be polynomials. I want to be able to study functions like this and call them rational. Is the denominator a polynomial? Yep, so it's a rational function. X plus the inverse of x. Is that a rational function? I'll pause for a second and let people think. And let's see. Folks for yes? Folks for no? Folks who hesitate to hazard a guess? All right, well, let's talk through it. What does x to the power negative 1 mean? Yeah. 1 over x. So what does this mean? This means x plus 1 over x. And maybe just to be extra leading, you could write that x as x over 1. I see two fractions added together. When you see two fractions added together, can you turn that into a single fraction? Yeah, what's like the buzzword for the thing you need to do? Yeah. Get a common denominator. What is that common denominator in this case? So, good. Rewrite this first term as equals. Not a very good equal sign. X squared over x plus 1 over x. Now that they have the same denominator, I can add fractions. All right. So now that we've done that bit of manipulation, is the numerator a polynomial? Is the denominator a polynomial? Is it a rational function? Yep. So here's the payoff. If I add together two rational functions, the result is still a rational function because you can get a common denominator and add fractions. What do you think if you subtract or multiply or divide rational functions by each other? Will you still have a rational function? Yeah, if I add fractions together, I can turn it into a fraction, a single fraction. If I subtract fractions from each other, the same thing. If I multiply fractions by each other, well, you just multiply the numerator, multiply the denominator. And if you divide, same thing. I guess there's like an extra hole in the domain, but otherwise you're fine. So with that in mind, look at that last example. Is it a rational function? Could you write that as a single ratio of a polynomial divided by a polynomial? Folks for yes? Folks for no? And it would be kind of annoying to actually do the arithmetic to do it. So since I don't need to do anything with this example as we proceed, I'm not going to. But yeah, this is also a rational function. Well, I guess I've just been putting check marks next to the ones that are. They're all rational functions. So I guess maybe this suggests that everything is a rational function. Can you think of a function that you know that maybe cannot be written as a fraction? Yeah. Where the denominator is supposed to be 0. Yeah, okay. It's like x plus 1 over 0. That would definitely not be a rational function. What's the domain of, is this function ever defined though? So, technically yes, that is an example of a non-rational function. It's also like a function that's just never defined. Yeah, it satisfies the conditions. I'm going to refine the question. Can you think of something which doesn't seem to be a rational function, which doesn't seem to be a ratio of polynomials, and which has some things in its domain. Cool. Well, we'll think about that for a little bit. And, well, yeah. Yeah. This is an example of something that is not rational. And there are lots of others, but maybe there's like a good example to keep in mind of something that can't be written as a fraction. Cool. So, let's carry on. So here's something to point out. You should always simplify your fractions. Just like you would never say 2 over 4 and like have that be the final answer if you want to actually do anything with this thing you're thinking about. You'd simplify it to 1 over 2. Similarly, if you want to see x squared plus 1 times x minus 2 all over x minus 2 times x plus 1, what does that simplify to? Yeah.
X squared plus 1 over x plus 1.
Yeah. So, when you can, you should cancel common factors. You should make sure the numerator and denominator are co-prime. Sometimes that's hard to do. Factoring a polynomial is sometimes difficult. But at least when the degrees are small, you should make sure that that doesn't happen. Graphs of rational functions. So, here is the graph of one rational function that you should recognize. Here's the graph of y equals 1 over x. It is what it is. We've seen lots of things about graphs of polynomials. Tell me something that distinguishes this from the graph of a polynomial. There are few. Yeah.
Splits off into 2 and doesn't look like it oscillates the order.
Yeah, so here are some things to think about. It splits off into 2. The graph is disconnected. Maybe I'll say it this way. At x equals 0, there's a pretty big jump. There's a discontinuity at x equals 0. If you picture the graph of a polynomial, does it ever have any discontinuities? Are there any breaks in the graph of a polynomial? No. So there's one thing. Maybe I'll say something similar related to that. If I give you a polynomial, so a sum of powers of x, are there any numbers you cannot plug into such a formula? So what's the domain of something like this polynomial? All real numbers. What's the domain of 1 over x? Yeah. X can't be 0. This has a hole in its domain. There's a number you can't plug into it. Polynomials don't have holes in their domain. You said x not equal to 0. That'll do. I guess if you like intervals, you could write it that way. The point is, it's not all real numbers. Polynomials have domain equal to all real numbers. Here's a way of seeing that this particular rational function is not a polynomial. Folks feeling pretty good? Nice. So, the thing I want to start building up is let's continue to think about details of graphs of rational functions. So, let's talk about those holes in the graph. Rational functions can have only fairly specific jumps in their graph. So if you have a rational function p of x over q of x, which is in reduced terms, meaning that p and q have no common factors, we'll have no jumps in the graph, except at the zeros of q of x, where the y value on the graph will shoot off to plus or minus infinity. So, there's a lot happening in that sense. So what is it saying? It's saying, boss, if you have a rational function, and you've already checked the numerator and denominator don't have any common factors, then the graph will be nice and smooth and continuous, won't have any jumps, except when you divide by 0. When you divide by 0, you'll see a really big jump in the graph, where the y values will shoot off to plus infinity or minus infinity. That makes some sense? And we saw that with 1 over x. There's only one hole in the domain. It's when x equals 0, and at x equals 0, you see the y values getting really, really big. That's true in general for any rational function. And there's a special word we'll make up for it. It'll have the word asymptote involved. So here's again the graph of y equals 1 over x. Let's talk about asymptotics. So an asymptote for a curve is a line for which the distance between that line and the curve gets really, really small when you look really far along the line. So there's the graph of this rational function 1 over x. Are there any lines that it seems to get close to when you look far along the line? Yeah.
All of them depending on where you look at.
Ah, all of them. So let's draw, I don't know, this line. It does cross the graph, that's true. But if you look just really, really far out along the line, because that's what asymptotics say to do, you only look at things far away. Does that line, as you go really, really far along, and get close to the orange graph? No. So this is an example of something that is not an asymptote.
I thought I was talking about like the slopes of the interface.
Ah, yeah. So it does certainly cross them. So like if you look near those 2 points, that line is really close to the graph. That's true. Excellent. So what are some lines that it does get close to for values far along those lines? Yeah.
X equals 0 and y equals 0.
X equals 0 seems to do, and let's, I don't know, draw a picture. There's x equals 0, and 1 over x goes on like that. If you go far along enough along the x-axis, does that line seem to get really close to the graph of the function? And you said also y equals, oh, that was y equals 0. The other one is x equals 0. So, here's the graph of 1 over x, find its asymptotes. It appears to be y equals 0 and x equals 0. And for rational functions, we'll mostly be interested, not exclusively, but mostly be interested in the 2 types of asymptotes. Vertical asymptotes and horizontal asymptotes. And the names mean what they look like they should mean. A vertical asymptote is an asymptote that's a vertical line. A horizontal asymptote is an asymptote that's a horizontal line. During the homework, we'll do some things today about slant asymptotes, which are asymptotes that are other lines. But let's not talk about those right now. So for this function, which of those 2 asymptotes is its vertical asymptote? Yeah. X equals 0. Which one is the horizontal asymptote? Yeah, the other one. So, I'd like to get the following understanding check. So, I'm going to give you some conditions. You are going to sketch for me a graph that satisfies these conditions. There's not enough here to pin down a unique graph, so results will vary. So sketch for me a graph which has a horizontal asymptote at y equals 2. So I'll draw some of these lines, y equals 2. And vertical asymptotes at x equals 3. I know green isn't totally clear, but I think that's okay. And x equals negative 2. Sketch for me the graph of a rational function that satisfies those conditions. Your results will vary. And while that happens, I should take attendance. The recording? Okay, didn't point it. So, I'll sketch a graph, and I'll see if anyone has any objections to this graph. So, let's see. We need to get close to this horizontal asymptote, so let's draw that. Maybe I'll have it do this. there's some graph. Anyone have any objections to that as an example? What objections do you have?
It goes to the horizontal asymptote.
It goes through the horizontal asymptote. And that is exactly, I drew this example to bring out exactly that objection. Because here's a fact. Graphs can cross their horizontal asymptotes. That's allowed. They don't have to. Like we saw 1 over x doesn't ever touch its horizontal asymptote. But a function can cross its horizontal asymptote. Horizontal asymptotes don't disallow that. To be a horizontal asymptote just means when you look very far along the line, the graph stays close to that line. It's allowed to wiggle around when you're not far along the line and can cross through that line if it wants to. That's permitted. So excellent. So there's an example. And people drew their graphs as though they didn't cross the horizontal asymptote. That's fine. That is also allowed. You're allowed to not touch the horizontal asymptote if you don't want to, but you're also allowed to touch it if you do. Any questions right now? So, yeah.
Can you find horizontal asymptotes?
Yes, absolutely you can. And we will here. So let's build a little bit more intuition by looking at some more graphs. And then we'll put that on the next page, I guess. So, let's talk about vertical asymptotes first. And we've talked about vertical asymptotes a little bit already. So there will be this thing where the y values shoot off to plus or minus infinity whenever the denominator is 0. So if p of x over q of x is in reduced form, then p of x over q of x will have a vertical asymptote whenever q of x equals 0. And this bit about being in reduced form is important. You should check that before you use this. If it's not in reduced form, a thing that you think might be a vertical asymptote, you might not actually have a vertical asymptote. We'll see that in one of these examples. If p of x over q of x is in reduced form, then there will be an x-intercept whenever the numerator equals 0. So let's use those conditions to find x-intercepts and to find vertical asymptotes. And hopefully the thing about x-intercepts makes perfectly good sense, right? To have an x-intercept means that the p of x over q of x would have to be 0. Only way for a fraction to be 0 is if the numerator is 0. And you don't divide by 0. 0 over 0 just isn't defined. So let's use that to find some things. So let's find the vertical and vertical asymptotes and x-intercepts of this. So if I want to find the vertical asymptotes, then what is it that I should set equal to 0? Yeah. The denominator. To find the vertical asymptote, you should set x minus 1 equals 0. That look easy to solve? Yeah, x equals 1, I think. What about to find the x-intercept? What do you set equals 0 to do that? Well, I guess even if you don't remember the trick that's listed here, you could set the whole thing equal to 0. X plus 1 over x minus 1 equals 0. If you wanted to solve that for x, what seems like a reasonable thing to do? Yeah. Yeah, just set the numerator to 0. From this point of view, that would mean multiplying both sides by the denominator. But that's just 0. So that's why to find the x-intercepts, you just set the numerator equal to 0. When is x plus 1 equal 0? Excellent. Think the remaining examples are doable? So I'll give you 2 choices. I'll keep talking through some of them, Or I can cut you loose and we can come together. Should I keep talking? All right, I'll keep talking. Let's go through some of these next examples. Here is another rational function. Let's try to find its vertical asymptotes and its x-intercepts. Let's start with the vertical asymptotes. And we'll sketch a graph to see what it looks like. What do you need to set equal to 0 to find the vertical asymptotes of this thing? Yeah. Denominator. X squared plus 1. So to find the vertical asymptote, set x squared plus 1 equals 0. And so we're thinking about graphs. We only want real solutions. We're not trying to graph complex things. What are the solutions? What are the real solutions to x squared plus 1 equals 0? Or alternately, just what are the solutions? Not 1. Plus or minus I. Yeah, so if you wanted to solve this, you would say, well, that means x squared is negative 1. X is plus or minus square root of negative 1, so plus or minus I. So on the one hand, that means that if you were to think about what the graph of a complex function should mean, there would be these vertical asymptotes of plus or minus I. The trouble is to visualize the graph of a complex function, you need 2 dimensions worth of inputs and 2 dimensions worth of outputs. So to graph a complex function, you somehow need 4 dimensions to work with. It makes it hard to visualize, not impossible. There are some really cool heat maps for complex value functions, but I'm getting distracted. There are no real vertical asymptotes. There are no, and I'm putting the real in parentheses because I wouldn't require that word. No vertical asymptotes. Let's find the x-intercepts. What do you need to set equal to 0 to find the x-intercepts? Yeah. Numerator. Which ones? So I should set x squared minus 1 equals 0. What are the solutions to that? Yeah. 1 and negative 1. That's right, if you want to do the actual walk, you would add the 1 to the other side, take the square root of both sides, but whenever you want to do a square with a square root, you lose information. That was quick, but people happy? Any questions about those 2 examples we've just gone through? All right, so this one I am going to make you do. Find the vertical asymptotes and x-intercepts of x squared plus 3 over x minus 1. Then we'll talk through this last one together. We'll get a long answer and then a right answer. Some Desmos graphs, I think. All right, so people feel like they have some answers just to that one? Where are its vertical asymptotes? Yeah. At x equals 1. Oh, I said x-intercepts, but the first one's vertical asymptotes. Yeah, there is vertical asymptotes. Did I? Oh well, the point stands. The vertical asymptote is at x equals 1. What about its x-intercepts?
Yeah. Plus or minus 3i.
X-intercepts at plus or minus 3i. On the other hand, since like you would want to graph the thing, if you wanted to graph those and see those x-intercepts, you would again need to figure out what a complex graph should mean. So on the graph, we should see no x-intercepts because we're only going to graph the real part of this. This last one, x squared minus 1 over x minus 1. So let's see what happens. I'm going to do something wrong, and then we're going to do something right. So here's the wrong thing to do. The wrong thing to do is exactly the things we were just doing. If you wanted to find the vertical asymptotes, you would set x minus 1 equal to 0. Fair enough? What's the solution to that? X equals 1. If you wanted to find the x-intercept, you should set x squared minus 1 equals 0. And we've already seen that. That should be x equal to plus or minus x equals 1 or x equals minus 1. So just in terms of seeing that answer, is there anything strange about it? Yeah.
Well, if you put in 1, you get 0 on both halves. Just zero outcomes. So there is no vertical asymptote.
It's worse than that. So you would end up with 0 over 0. So there isn't a vertical asymptote there. So this is just not defined. There's also not an x-intercept there. Let's see that looking at the graph. Let's graph that function, and we'll see if we make any observations. So here are the graphs of each of them. In particular, there's the graph of x squared minus 1 over x minus 1. What does that graph look like? Yeah.
Slight asymptote.
It looks like a slant asymptote, but more than that, it looks like just a straight up line, right? So I think this thing simplifies. Let's go back to this example. The numerator and denominator, do those have any common factors? X minus 1. The numerator of that thing factors is x plus 1, x minus 1. So, all this is wrong. The right thing to do would be, well, x squared minus 1 over x minus 1. That's x plus 1, x minus 1 over x minus 1. So, I see a common factor that cancels. What does this actually just equal to? X plus 1 on the nose. All right. So, this function now, x plus 1. Tell me about its vertical asymptotes. Does it have any? No, there is no denominator set equal to 0. So it's got no vertical asymptotes. Where is its x-intercept? Yeah. X equals negative 1. Right? You would just set that thing equal to 0 and solve. So that example is just reinforcing that this condition, that these things need to be in reduced form, matters. You should check if your rational function has any common factors in the numerator and denominator before you proceed. Otherwise, you might get this weird situation where you see an x-intercept where there is also a vertical asymptote. You can't have both at the same value. If you ever get that as your resolution, you know you failed to simplify. So if you ever see a vertical asymptote and an x-intercept at the exact same value, go back and cancel a factor and try again. Any questions right now? Cool. So, you know what? And because horizontal asymptotes were asked about explicitly, let's talk about how to find horizontal asymptotes. And we'll give like this looks like a complicated many-line theorem. I think I'll give the idea of it first. So let's give the idea of this. So if you want the horizontal asymptotes of, let's actually just grab one of the examples down at the bottom. X to the fourth plus x squared plus 1 over negative 2x to the fourth plus 2,000 x cubed. So to find the horizontal asymptotes of a number, let's imagine what would happen if you plugged in a giant number for x, a 20-digit number for x. If you did that, so to think about that, plug in x equals, I'm going to put quotes here, big, because no matter how big you plug in, I really mean plug in something bigger than that. So let's imagine you plug in something gigantic for x, 20-digit number. This would be an 80-digit number plus a 40-digit number. Does this 40-digit number make any difference compared to the 80-digit number? No. Does that plus 1 make a measurable difference? No. Same thing in the denominator. So when you plug in something really, really big, you'll get basically x to the fourth over negative 2x to the fourth. And what does that simplify to? Yeah. 1 over negative 2. Well, negative 1/2. You should put the negative sign in the numerator. Negative 0.5 if you prefer. So, the horizontal asymptotes of this are at y equals negative 1/2. So one way of thinking about horizontal asymptotes as an idea is imagine you plugged in something gigantic. Then only the biggest thing in the numerator and the biggest thing in the denominator matter. And that's enough information. Let's see that let's see what that means in practice. So let's suppose you have a rational function. The degree of q is bigger than the degree of p. So you saw like x squared plus 1 over x cubed minus 50. Let's see what would happen there. If you want to plug in a giant value for x, does that plus 1 in the numerator make a difference? Not much of one if you plug in something giant for x. Does the minus 50 in the denominator make much of a difference? Nope. So this will be basically x squared over x cubed, 1 over x. Oh, cool. And if you plug in something gigantic for x, a 20-digit number, then what will 1 over x be close to if you do that? Yeah, just say it louder there. Someone whisper the right thing. I think. Yeah, 0. Whenever you have the degree of the denominator bigger than the degree of the numerator, the horizontal asymptote will be at 0. Whenever the degree of the numerator is equal to the degree of the denominator, whenever these two have the same degree, so let's think about x squared plus 1 over x squared plus 7, x. Let's play the same game. If you want to plug in a gigantic value of x, let's put some coefficients in one of those, 3 and 2. Does the plus 1 in the numerator make much of a difference when you plug in a gigantic value for x? What about the 7x? Does that make much of a difference? No. If you're plugging in like a 20-digit number, then 3x squared is 40 digits. Who cares about a 20-digit number in comparison? Ignore the little order terms. This is approximately 3x squared over 2x. And what, squared. And what is that? Yeah. 3 over 2. So, and notice, this 3 just came from that 3. This 2 came from that 2. If they have the same degree, then the horizontal asymptote will be at the leading coefficient of the numerator divided by the leading coefficient of the denominator. If you plug in the case that the numerator is bigger than the denominator, then the opposite would happen. So in this first example, instead of getting x squared over x cubed, you would get x cubed over x squared. That doesn't get close to a horizontal line at all. there is no horizontal asymptote if the degree of the numerator is bigger than the degree of the denominator. Those conditions make some sense? And if you don't like memorizing conditions like that, just remember, horizontal asymptote means plug in a giant value for x. Plug in that really big value, see what happens. And I think we have time to read off some, and then we'll do some graphing on the next page, I think. So let's read off the horizontal asymptotes for these examples. X to the fifth minus 1 over x to the fifth plus 1. Here are 1. Why 1?
Leading coefficient of A is 1. So B is 1.
Yeah, the leading coefficients are both 1, and they have the same degree. So the horizontal asymptote will be at y equals 1 over 1, also known as just 1. Feel good? Bottom left, where is that thing's horizontal asymptote if it has 1? Yeah. 0. Yeah, so why 0? Yeah, excellent. The numerator is degree 4, the denominator is degree 5, the denominator will win. Last one, x to the fifth minus 1 over x cubed plus 1. Where is its horizontal asymptote? There is no horizontal asymptote. Instead, if you wanted to think about what happened when x is big, you could do long division to see the actual asymptotics. And to talk you through that is a homework problem. Groovy. The homework problem posted for today. Any standing questions about this idea right now? Nice. Then, let's... no, we need to do some long division for the sake of that homework. Let's do some long division. So let's try to graph this function, x plus 1 over x minus 1. And let's try to do it directly using the idea of transformations of graphs. So to do that, I guess I need to compute x plus 1 divided by x minus 1. I guess we need to do polynomial long division to do that. It won't be very long division. So if you want to compute x plus 1, you want to know how many times it goes into x minus 1. Let's do that. Excuse me. So, look at the leading terms first. What do you need to multiply by x to get x? Yeah, just say it that way. 1. Yeah, perfect. Then you take this, multiply it by that, and subtract. Minus x minus 1. Negative 1 minus 1 is negative 2. The remainder is negative 2. And you expected a remainder this time. Let's see what that means. That should mean x plus 1 over x minus 1 is the same as 1 plus remainder of negative 2 over x minus 1.
Why are you dividing the denominator by the numerator?
Did I do the wrong one? God damn it. God damn it. Yes, it should be. Thank you for pointing that out sooner rather than later. I guess it's an easy, well, no, gotta fix it. This is why my pens have erasers. And that is absolutely something that I am bad at keeping straight, especially when they're both like the same degree. So, all right. The one on top should be the one in the box, right? Yeah, the one on top is the one in the box. All right, follow the same algorithm. I think you get the same thing, but the remainder is 2. Awesome. 1 plus 1 over x minus 1. All right, x plus 1 over x minus 1, 2, is equal to 1 plus 2 over x minus 1. Here's the reason why I did that. Now it's actually correct, right? Okay, that's good. I claim that I can read off exactly what the graph of this thing looks like via transformations. Because I could rewrite that as 2 times 1 over x minus 1 plus 1. That looks like a slightly asinine way to write it, but now I see transformations. That looks like I should start with the graph of 1 over x. And what will that do to the graph of 1 over x? Make the points wider. It'll make it taller. You're multiplying the outputs by 2. So it'll get twice as tall. Then it will go, what does that minus 1 do? Goes to the right by 1. It's done to the x, so it does the opposite of what you think. And then what will that plus 1 do? Up by 1. So this will look like the graph of 1 over x. Then you stretch it vertically, and then you go right 1, up 1. So I think that will move the asymptotes right 1 and up 1. So by doing long division, you can see exactly what the graph of a rational function will look like by transformations. That's the point of this. And also, I guess, to remind you that when you do long division, you should do it right instead of wrong. So, what will we pick up with next time? We'll pick up with something that will seem very familiar. If you have already factored your rational function, it's easy to graph. And if you remember, if you have the graph, a polynomial that's already factored, it is also easy to graph. Same idea here. Neato. If you didn't grab the note packet, then there's one. If you didn't grab the review for the midterm, they're there. You too. I accidentally swear in this recording?
I don't know.
I think I probably did.
Is God damn it a swear?
Yeah, I think probably it would get you demonetized on the YouTube, but fortunately I'm not monetizing these.
That's a good thing.